Hi there. This is a presentation that introduces the discipline of design. Design is a massive topic, and it is one that can't be fully taught by simple lectures or reading of books. It must be learned by doing lots of practice. However, there is value in reading books, in listening to lectures, in thinking about the process and the product that comes from design. This is that introductory lecture that I hope will set you on a way towards being good designers. So I'm going to try and cover a fair bit on what is design and how it's seen by different players in the industry, particularly the building industry, but with reference to other industries that use design to solve problems. Then I'm going to talk about how to do it and more about why you should care how you do it in a way of getting to an answer. This question of what is design is actually more important than I think many people give it credit. Understanding what design is will help you in terms of being a better designer and evaluating the quality of designs that are placed in front of you. So, very simply, and more universally, design is a problem-solving activity. At the end of the day, that is what we designed for, is to solve a problem. A great textbook by a number of University of Waterloo professors called The Discipline of Design. And in it, a more formal textbook type of definition is given. Design is an activity which usually begins with the perception of a defect or lack in some part of the human environment and ends only when that defect has been rectified. And that's intentionally a very broad and formal definition. So whatever you want to define and how you tweak those words, at the end of the day, design is a fundamental part of engineering and, of course, also of the practice of architecture. Now, one has to also recognize that design is an activity, meaning a verb. Design can also be a product. That car is a good design. But design is also the set of drawings and specifications that are used to make a product. So design has a number of overlapping and correct definitions and uses in the everyday language. But one thing that's important to recognize is that design is not an aesthetic activity alone. Obviously, aesthetics play an important role in many design decisions. However, design is much deeper and broader than that. So, just to start with, as I said, design is a problem-solving activity. So design is not something for sport or entertainment or spiritual upliftment. Design is solving a problem. And since we're talking normally about humans doing the design, it is a design of a human concern. So when you're doing a design, the major activity that one does as you follow through the process is you're making decisions. You're solving the problem, but making decisions about what's important, what's not important, what the problem is, what the problem isn't. All of those things are decision making. And so a lot of the theory of design is actually, when they study the process, they realize it's a decision-making analysis that needs to be done. How do you make the decision at every step of the way? And there are many decisions in real designs. Now, it's also a constrained decision-making process. So one of the things that differentiates design from, say, art is that design has constraints. You don't have a lot of time. You don't have enough knowledge. You don't have enough money, etc. You can't make it beyond a certain weight. It can't burn. all kinds of constraints, of which there can be identified many hundreds and thousands for most common products that are designed. And that includes buildings. So design can be applied to the process of planning. You're planning a path from your current location to the nearest Starbucks to get a coffee. That could be a design process because you're solving a problem by making a series of decisions, and maybe you remember your decision for that design, or maybe you even write it down as a series of steps for someone else to go get you that coffee at the nearest Starbucks that you know where it is. So the design process almost always involves those types of instructions and planning. And also, it can be part of creating a thing. Most of the challenge of modern technical design is that we separate the creation of the object from the design. So there are two separate stages. You design the shape of, say, the binocular case, and then you have to design the process by which it's made, and then you actually do the execution of making the case for the binoculars. And in the building industry, we design the building, and then we design the process by which it will be constructed. And then there's a lot of executing of actually building the building. And during that process, in real life, we find out that we maybe haven't totally sorted out the design, meaning what is the building, or we haven't totally designed the construction process, that is how we will build it. So we have to continue to make decisions during the construction process, which is actually an extension of the complete design process because we aren't done yet. So if we want to describe what design is in sort of maybe a more applied way, another tact we can take is to say that the design of physical objects, as opposed to systems or software, it involves the selection of materials, forming or shaping them, and then arranging them to meet a particular purpose, to solve a particular problem. So let's go over that. Select materials, form or shape them, arrange them relative to each other to solve a problem. That is much more of a description of the building design process right there. Now, there are numerous books which I would welcome you to read, and I have at least 50 of them, on the design process, technical design, engineering design. And they all have variations on this theme, and it's worth thinking about and understanding those different variations. But I'm going to move on now from the definition of design, and I'm going to start looking at some examples and some case studies. So a pretty old, in terms of human history, design of a tool is the axe. It's very basic. It's been around for tens of thousands of years in the archaeological ruins of human habitation. And it solves a common problem. But I think we have to be careful that when you look at the designs for axes over the last 10,000 years, you will find that there are a lot of different designs. And if you look at the designs that are available today by doing an internet search, you'll find there's also a large variation. So why are there so many variations if they're solving the same problem? Well, the first step there is they aren't solving the same problem. Certainly, the types of axes we have today are quite carefully designed for very particular problems. So there is the firefighter axe, which is meant for chopping through walls and roofs and car doors in terms of freeing someone from a wreckage or a fire, which is a very different type of axe than would be the type used to split pieces of wood into smaller pieces. There's wood that's meant for peeling the bark off of trees. There are types of axes that are meant to split large and difficult to split, not filled chunks of wood. So we end up with a whole bunch of different solutions. One of the nice things about looking at these design solutions is that even with that range of problems that they're solving, there's a couple things that are actually quite common. You'll notice that the handles for many axes to this day are still built out of wood. Now there's some axes, one on this slide, that have fiberglass or some sort of composite handle. And that has some pretty interesting advantages that it conveys. But one of the reasons that we see an awful lot of wooden handles in modern axes is that wood is actually a pretty ideal material for an axe handle in many regards. And it turns out to be quite inexpensive. If you want to improve on wood in the handle, you actually have to spend an awful lot of money to come up with some special composite. And even then, you're not always convincing all users that the axe handle is better. But we have these alternate solutions because of different problems being solved or different constraints. So the constraint for the axe makers of old was that they did not have access to carbon fiber composites. The constraint of many axes down the history have been that we didn't have a lot of money per axe, so we used what we could given a price limitation. Or we didn't have the technology, even if we had the entire resources of a kingdom to make the perfect axe, we just didn't have the technology. And those are common constraints, is money and technology, or sometimes time. These are common restrictions that limit the possible design solutions available to you, the designer. And it's really useful, some would say critical, that you actually understand the constraints quite clearly. Technical or engineering design is a subset of design. But what makes it a subset? Well, it uses some sort of rational decision-making process, meaning by rational I mean you can explain why you've made the decision and that you would get the same decision every time when you followed that path. It often uses analysis, where we assess how a design solution is likely to work, how much it's going to cost, how long it's going to take to build it, etc. And those quantifications are an important part of engineering design. Now, that's not to undervalue the fantastic design that is routinely produced by very skilled and experienced artisans who can look at a problem and, without being able to fully explain it, can come up with a design solution. But that's not engineering design. And increasingly, we make decisions in the world that have such significant ramifications from a point of view of health and safety, from environment, from cost, that we're not willing to just trust that one person's experience and genius. And this is where we come into the need for more and more technical design, where we have a rational, science-based approach to making decisions, and we can quantify the choice of these decisions. So, although engineers have the hallmark of using the results of analysis, usually quantitative analysis, to guide their decision-making, judgment and intuition remains critical. And this is something that's easily forgotten, but it's partly because it's really hard to teach judgment and intuition. The best way to get judgment and intuition is by experience, which means doing a bunch of designs, evaluating their success. And of course, since we can't do all that many designs, we learn the most by looking at other previous designs that are similar and try and understand what resulted in that design quality, good, bad, indifferent, and how would that sort of decision making influence my current design. So I can go from an axe, which is a pretty simple design product, to a commercial airliner. And as an example, these are all done by engineering analysis today and have been, largely guided by engineering analysis literally since the beginning of aircraft, at least since the Second World War. And one of the things I hope you can take away from looking at these highly engineered and quantitatively analyzed systems is that they're very similar. When you set up the constraints about price and safety and manufacturability and high altitude and low altitude and hot and cold and fast and slow, you end up with machines that have this shape. And even though there's a broad range of sizes between the Bombardier C series, which has been purchased by Airbus, and let's say the Boeing 737 or 787 in the upper left corner, they actually have an incredible amount of similarity. Actually, you can argue they have more similarity than modern axes. And that's partly because modern axes actually solve a broader range of problems than do modern airliners. So the use of rigorous decision making will often end up with coming to similar conclusions. This is not bad design or a lack of creativity. This is good design, and it is showing that the type of solutions might actually properly be very similar. So trying to steer a design in a different direction, or sometimes we use the term innovative, that's dangerous because it could push you away from the best design. Just to be different doesn't usually solve a problem. Now, if the problem set before you by the client is that you produce something that's different, well, then immediately that becomes a goal. The product may be inferior in solving other problems, whether chopping wood or flying passengers. But hey, if somebody said different was important, then it, by definition, needs to look different. But the opposite is not true. Different isn't often better, and different isn't not being different isn't a lack of creativity. It really can mean that was the right decision, and that is the right decision no matter how you approach it. I also wanted to just look at a couple of engineered products. What's kind of interesting about this is that this is the International Space Station. I'm saying it's $100 billion US, but that's lowballing it. It depends a little on how you count the dollars. But it's been built over a period of 20 years. It happens to be in space, which makes things expensive because it's hard to get there. Expensive, really. And we don't have a lot of wiggle room to be wrong. So as a consequence, this is highly engineered. But of course, it is a designed product. But it's the kind of product that relying on people's seat of the pants to say, I think it should be this thick, is not going to work. No matter how experienced you are as a spacecraft designer, in this type of a process, you will not be allowed to say, I think it should be this. You're going to have to prove it. And that adds a lot of time and complexity to be able to do engineering, design, and analysis. And I think engineering and design analysis would be completely appropriate here. But by the same token, don't believe for a minute that these types of systems, as important, as expensive as this is, that someone does a computer model and says, this is the right answer. And they have three-dimensional, beautiful everything. And you know what? No one's going to believe it. They're going to rely on experience from other projects around the world to make sure that your design is similar to them, and where it's different, it's explicable. And then they're going to build at least one and probably several mock-ups and prototypes and test them to destruction before they undergo the effort of sending it to space and putting lives on the line. So analysis is never sufficient. It's always backed up by experience, testing, real-world assessment. Now, whether or not the International Space Station is designed or engineered may seem not important. But there are reasons to consider what it means to engineer something versus design it. And part of those reasons have to do with the law, in that when we are being asked as professional engineers to design a building, it often does rely on engineering, which means some analysis, some rational method, and compared to physical laws, following the physical laws, comparing to physical performance. There's an expectation in the law that when you are asking for an engineered design, that is the process. You can't rely on what your gut says or what your heart demands. This is another expensive object. I'm just showing it closer to Earth. And many of you may not realize, but these types of offshore oil rigs routinely cost more than $5 billion. And a majority of that money is tied up in engineering the manufactured object, and very importantly, the process by which that product is created and delivered and brought online as a functioning object. This one happens to be in Canada's offshore area on the East Coast, Hibernia, and it's a $10 billion. It's a bit more expensive because A, it's big, and B, the weather sucks. And so dealing with icebergs and ice storms and hurricanes and all the rest of it means that these offshore oil rigs were very expensive. But also, as we move to a world where burning and extracting carbon is less and less desirable, I hope you can see that we have developed the technology and the design ability to solve some pretty incredible problems, and the ability to generate the funds, $10 billion in this case, to justify them. And so some of the newer low carbon technologies seem like they're rather exotic or rather expensive or rather large, but that's only in comparison to, say, everyday life, not in comparison to the fossil fuel industry, which has taken on the largest, the most expensive, the most technologically demanding problems up to and including spaceflight. So we can apply the same design and technology for other reasons. Get to, say, more normal buildings, then we end up in the range where they're only about $1 billion or so. The two buildings on the left-hand side of the screen are in downtown Toronto. They're in the $1 billion mark area. And we know this because they've been sold to different, and the public numbers are available. The Singapore Hotel in the upper middle, that's probably a close to $5 billion project with a swimming pool at 40 stories above grade and, thousands of hotel rooms, etc. In the bottom middle, we have what I consider an ordinary stadium, but that project was over $1 billion when it was completed about 4 years ago. And on the right-hand side is a relatively famous Burj Khalifa, which is the world's tallest freestanding building right now. And we don't know the full price for that, but definitely more than $1 billion, probably a couple billion. So when you have projects of this scale, you can imagine that design is almost always engineering design. Whichever profession did it, whether it's architecture, technologist, whatever, we need to use rational analysis and quantify our decision making to justify the expense and reassure the investors that the expense is going to be protected. Now, obviously, we have much smaller products in the building industry. On the upper left-hand corner is a house which I'm putting a price of $125,000. Today, you'd be hard-pressed to find any house that's only $125,000. But this was a pretty simple house in Tarboro, North Carolina, and so and it was 10 years ago, and it was less than $125,000 at that time. Upper right, simple house in the outskirts of Waterloo. Today, that house is probably $500,000. But obviously, in the lower parts of the slide, we see a couple of houses that are for obviously exceptional applications. And so these are millions of dollars. The one on the bottom left is in Italy. The one on the bottom right is north of Toronto. It's Timothy Eaton's house. So a little bit more about design, and then we'll get into the process. There's a couple of quotes here I collect from various famous designers. And Steve Jobs of Apple fame said, design is not just what it looks like and feels like. Design is how it works. And this should be something that you take on board if you are an engineering type designer, because it really does matter how it works in terms of influencing the design. So also, as I'd said earlier, that we're not trying to create something new per se, meaning the goal of a design project is not to come up with something new unless something new would make a better solution. And so in many cases, there's something different about the problem you're working on. And if it's a slightly different problem, you'd expect a different solution. Similarly, time goes on, we learn more, we developed new technologies and understanding, and so the new design will often look different than the old design for very good reason, because it'll have taken on board that new knowledge and that new understanding. Now, you need to know how to do something better, and that's what a good design would be. And another Apple designer, Johnny Ive, who says different and new is relatively easy. Doing something that's genuinely better is hard. That's very true. And when you go into the design of a product, whether it be a chair or a house, you should be fully aware that many, many people have looked at the design of a chair or a house before. And you have to ask, why should my design be different? What about my design problem or my constraints or my available resources is sufficiently different to come up with a sufficiently different chair or house or whatever? So the problem of people creating new and innovative designs is so widespread that there are actually websites and articles devoted to this phenomenon of people trying so hard to be different that their designs become bad to, in this case, ludicrous. And so, wow, this is a very cool looking door. It's a completely impractical door. Or, although this is a new approach to a key for a whole bunch of practical reasons, I hope you can recognize why this is a major step back in the design of keys. Wine glasses are cool. This definitely looks interesting, but is it actually solving the problem that wine glasses were meant to solve? Again, first look, very cool. Second assessment, what a disaster. This is not from that website. This is from an actual photograph of an actual product for sale. And it's not clear at all why this faucet in a bathroom would be helpful for solving the problem of washing your hands. In fact, that thin ribbon of water is probably in the exact opposite axis of where your hands would be, which would be left to right, not front to back. And it's not clear that the water wouldn't just splash all around and be captured, etc. So looks kind of interesting, probably doesn't really solve a problem. Here's another example of a table that looks really cool. And this is a real product. People make products like this. But although this is an effective table, you can see if that light stand gets pushed just a little bit too close to the edge, it'll fall off. And that curved edge is like you're not really sure when it falls. So, your pencil at some point, you put it one inch to the left and it falls off. So not a very practical design. You could come up with design solutions that limit that particular problem. Just another example of what looks like a cool chair, but almost certainly is a very uncomfortable chair. So these were all innovative designs, and all of them were bad designs. So make sure that your filter of doing something new is something that is better, or something that responds to new constraints, new resources, new problems. So I'd mentioned also that art and design are sometimes put in the same bucket, and we argue about what is design and what is art. But in most cases, a technical design, it's easy to say it must be functional. Art does not have to do more than entertain, inspire, provide pleasure to look at, whereas a technical design needs to solve a problem, needs to do something, fill a void. And that's a big difference between a painting and a piece of sculpture and a building or a car, where the latter two are technically driven with really clear functional performance expectations. So this brings us all to, let's now talk about the discipline of design. And that word was carefully chosen in the textbook because design is not some sort of lightning bolt from the heavens that inspires you. Design is something that is a process. And in fact, a lot of good design comes out of simply following through on a good process. That doesn't mean that creativity, inspiration, intuition do not play an important role. They do. But it's not just about inspiration and intuition, both of which can and are developable. It is actually a pretty clear process. So there are many sort of ways to break down the process, but I can tell you there are entire textbooks that explain this process, and some of them break it down into 27 steps, some of them break it down into 5 steps. I've sort of cribbed together, by reading all of those, a 5-step process that works well for architectural engineering and a fair number of other processes as well. But the first step, I think, is pretty clear, is defining the problem. And then you review previous design, it's called precedents. You look for solutions that might solve that problem. You evaluate your proposed solution, and this is where the engineering analysis, computer simulation, and various calculations come in. And then when you've decided that you have the best design you're going to come up with, then you document what that design is so it can be implemented. In our case, it can be built. What's important to you to realize is that there is a whole bunch of iteration, and that when we define the problem and identify limitations or constraints on the design, we don't just leave that forever. As we go through and look at previous problems that were similar and the design solutions, we may learn that, oh wait, there's these other restrictions, constraints. There are other problems that we need to solve at the same time. And that means you might then cycle back from step 2 to update step 1. And then you go to step 3 in terms of looking for solutions to the problem. Now, when you've searched for solutions, again, you may identify, and by search for solutions, I mean you create them, you look around the world for them that are exactly what's needed for your problem with your constraints. But you may end up having to go back and look for other precedents. You may have to go back and change some of the constraints. And that's why these arrows are important to say, sometimes you skip over and back and then revisit and adjust. And so the process isn't this simple linear thing. And I can't tell you how much time you should spend on each step. But I can say there is a reason to do every step. Some design projects will require you to spend a lot of time on one step and not much on another. And other design projects will invert that, and you'll spend a whole bunch of time on a different step and no time on that step. So let's just look a little bit at these 5 steps. The problem definition and identification of constraints is really important. Defining the problem is far more important than most people recognize. And so being able to say, really zoom in on what problem do we need to solve? This is often the place where genius comes in, is that people see a different version of the problem that hasn't been articulated or developed before. And so that sets them on the way to a really effective design solution because they had nuance in their problems. And in that problem definition, we're learning that you need to do this very much with an open mind and actively try and look at it from different perspectives. Some of the simplest examples of that I can give you is that don't design things that only work for right-handed people, because there are left-handed people in the world and not a small number of them. Don't design this for people who are 5'11" tall, because there are many, many people in the world, adults I should say, who are 5'2" tall. And if you intend to include children, then you now have to start designing for 3-foot tall people. And what about people who can't walk very well, or need a wheelchair or a walker with assistance, or use a cane, or have bad vision? All of those factors actually add constraints to your design solution and are a better refinement of your design problem that leads to better and different solutions. So just various perspectives is the best way of getting this. I'd mentioned that this is a well-known problem of not spending enough time defining the problem. In fact, there's at the University of Waterloo, which is the home to many startups, hundreds of startups, it has been observed that it is such a problem that they have created the Problem Lab. One of our faculty who had spent a lot of time in the startup world actually went out and raised some funds from Silicon Valley, venture capitalists, etc., to start this lab, because the problem is that people are not defining the problem. They come up with a solution as an app or a widget, and they've never spent the time figuring out what the real problem is. So you can go Google this, check it out, and actually it just shows the depth of how often this step is jumped over or given short shrift. Constraints are a critical part of your design. Depending on the constraints, the design solution could be a good one or a bad one, the exact same design solution. So when you're starting a project, not only do you need to define the problem very well, you also need to document the constraints. And really, it's helpful to write it down to keep it aware all the way through the process of what is constraining your design solution. And when you're doing that, you're often going to put some of those constraints in, collect them together, put them in buckets. Often you're doing this in a brainstorming process to say, what are all the limits on what you are allowed to do? Now, some of those limits that you can actually quickly identify and even quantify in many cases are things like cost and schedule and safety, regulatory compliance, skill available, knowledge available, technology available, materials available. All of those deserve to be on most design lists as constraints, because there's some limit on all of them. Now, again, I go to comparing art and design. This is a quote from David Pye, a famous author, who is just going through and saying the thing that distinguishes design or technical design, really, from such arts as painting and sculpture is that the practitioner of design has limits set upon his freedom of choice, meaning they can't just choose to make a very heavy object or a very large object or a very expensive object because there are real constraints. Now, precedence is step number 2. Step number 1 was the problems and constraints, identifying those. Step number 2 is look at what others have done before you. Learn from the successes and, just as importantly, the failures of others. So it's useful if you can find failed designs, sometimes hard, but certainly you can find successful designs that tend to be close to what you're working on. Just remember, before you can think out of the box, you need a box. And so that box is your precedence. How do people normally solve similar problems? So what we can do is look in other industries or at different scales as for what solutions have been done. Look at how people did it at different time periods, because you might get lessons there. Now, you need to analyze this and make sure that the precedents you're choosing, you understand which constraints are different, what has changed since that design, how different is the problem, and that usually explains why their design is not perfect for your problem. But identifying that difference is a useful thing and can help you come up with a better design. So now we have to go and look for solutions. And the solutions that you're looking for are often, they seem somewhat magical because they're pulled out of the blue sky. But they're not really pulled out of the blue sky. After you have done a good job of defining the problem, identifying the constraints, and exploring many precedent previous solutions, well, that's not blue sky anymore. You are now steeped in the design process, and many times then new solutions can be proposed. Now, when you propose a solution, you don't know that it's a good design. That's the thing that comes from nowhere, is the solution. And now you need to assess whether it's a good solution, which is why this quote from Thomas Edison, and actually he was a person who used a real process. He hired hundreds of people who went through and tried dozens and dozens of prototypes and variations on particular problems that they were working on. It was a complete industry to come up with invention. And this process was very much used by Edison. He says, "I have not failed. I've just found 10,000 ways that won't work." And each of those ways that don't work is useful information for others. So, as I've said, you're going to iterate between these levels, and that's very much something that happens as you're coming up with solutions, proposed solutions anyway. And also, you tend to go through, you propose a solution or 3, you pick one, then you get deeper into the one that you think is the best. And as you add detail to the design, you discover new questions that need to be answered, which may push you back to the problem definition, push you back to the constraints. So as we go from cycle to cycle, as we iterate through, we are going to make some of our designs worse. We'll make changes and we'll find out they're worse. And therefore we'll go back to the first design or try something else. But trying a bunch of solutions is critical, because we can often not be sure that a design solution is the best answer. The best we can do is to come up with 2 design solutions and show that solution A is better than B. You still don't know A is the best, but you now can be sure A is not the worst. And if you have 5 solutions, A, B, C, D, and E, you might say C is the best. A was almost as good, almost as good. E is a total dog. As soon as you start having multiple solutions to compare and contrast, you have a much better idea of the size of the solution space and where your best solution fits within that. So we often expand options as we begin the design cycle. Then as we analyze and compare to constraints, we weed some solutions out, tweak some solutions to have fewer, and then we go through another cycle of this. One of the realities that we've learned and documented about the design process, as we go through each cycle of design, we learn more because we've been working on the project. We learn more precedents. We understand more about the constraints, more about the problem. But as we work through, we also tend to have less freedom of design because we're running out of time and we're running out of resources, and we have to make decisions because we, at the end of the day, particularly engineers, we have to solve the problem. And so we end up learning more, but not always having so much flexibility anymore. So this is often shown in the building design process in these types of curves here, that early in the building design, we've got lots of possibilities, but it doesn't really affect the building in any way because we haven't designed anything. As soon as we pick a solution and start working towards detailing that solution, then our ability to influence performance and the amount of effort we can put in goes down. So we tend to have these curves, and this shows up in machine design as much as it does building design, is that the potential for big solutions is highest at the beginning and then fades with time, and the cost of making changes to your design keeps going up and up and up. Especially in the building world, if we start making changes at the construction stage, it's quite expensive. Step number 3, this is, the search for solutions. I can summarize here that we're going to have multiple solutions, and it's not enough to have one solution that works. We need numerous solutions so that we can compare them and rank them. The challenge in our design, because of this time factor, is that we want to get quickly into our design space, quickly evaluate rough designs so that we can more early in the process zoom in on viable, likely solutions. And this is what actually tends to happen in real technical design projects, is that we focus on the biggest bang for buck, most uncertainty at the beginning of design, leaving accepted and understood things to later in the design, where we have more, we know the answer better up front. So these are the subtleties of experience in design, design in a particular discipline, that lets us know, is this a good first choice or a bad first choice? What should I focus on? Now, one of the things I thought I should mention here is that in our design solutions that we propose, complexity is often a problem. In the modern world in particular, we have so many options for materials and systems. We have so many people involved, so many constraints that limit our designs, that just managing that complexity is a major deal. And that's why striving for simplicity at the early stages can be a very powerful strategy. And beware, just try and keep it simple at the beginning. I love this quote from John Gall, who, this quote, there's variations from various people, but he says, a complex system that works is invariably found to evolve from a simple system that worked. The inverse proposition also appears to be true. A complex system designed from scratch never works and cannot made to be worked. You have to start over, beginning with a simple system. And this is partly can come out of your assessment of precedence, but when you look at a modern car, there's no way that somebody could start to design a car with today's complexity of that car based on a clean sheet. It almost, the way the car developed was over generation after generation, 100 iterative design models where we kept adding this, adding that, tweaking this, improving that, removing a little bit of something. But that is how we end up with these complex modern projects. It's not a one-off. And when we try and come up with one-off new solutions that are that complex, John Gall says, and history would support him, is that there are very few successes. This level of complexity almost always fails. So step number 4, after you've sort of worked through a number of reasonable solutions to consider, is to evaluate that proposed solution. And this is where we will take you back to step number 1 and say, does it solve the problem you identified? Does it respect the constraints that you've identified? And that's how you know if the design is a good one. Is the one you proposed, does it meet those requirements? And how well does it meet those requirements at the beginning relative to another design proposal? And so this is where testing and simulation and calculation and analysis are used, because they're all trying to assess the performance of this product without actually having built it. So it's all done in computer space or paper space. And we say, using what we know about physics, can we predict how this object will perform? And then compare that performance to what the original design objectives were. As you probably can imagine, a lot of design is not amenable to this sort of quantitative analysis and comparison. So we have to come up with rankings, good, bad, indifferent, high, medium, low, stuff like that. Because a lot of things that matter in design, we haven't yet figured out how to put a number onto, or certainly not how to calculate. Now, once we're done and we've actually analyzed our design and can convince people that this is a design that solves this identified problem with these constraints, and here's my analysis as to why it does that. Now we need to document what that actual product is. So whether it's a hairbrush or a high rise, you now need to start making the drawings and the specifications that translate your concept of a design into a workable set of instructions for others to manufacture it. And that, in the building industry, drawings and specifications, which is why, in architecture and engineering, it said, we do not build buildings, we produce contract documents. Now, those contract documents are to make a building, but it's still not a building. So let's have some takeaways from this broad and long presentation that introduces you to the discipline of design. First, it is a discipline. There are steps that should and must be followed. You can improve the likelihood of good design outcomes if you follow these 5 steps or in the sub-steps within them. Beware just darting off to creating solutions and then asking what the problem is first. Beware getting trapped by, if it looks different, it's a better design. That's the innovation without purpose. Or skipping over steps because, I know all the precedents. Maybe you do, but then you should document them. And learn by practicing design, learn by observing other people doing design, learn by looking at design solutions and playing back in your mind, what were the constraints? What were the objectives of this design that led to this particular solution? Who thought this was the best idea? I do this a lot when I find not so great design solutions, like the sink in my hotel room, or the electronic projection setup at the School of Architecture. I go, who designed this system and why did they think it solved the problem? And many times, bad design is a consequence of the people who had a different problem than you thought. The problem they're designing for is making their job easy, or making the hotel room cheap, or making the electronic setup easy to buy and install, not easy to use. That kind of thing. So there's a lot of famous and quality books out there. I'm going to just show 3 here on the screen that are a broader range. The middle one is the true Bible of actual design thinking that applies to technical design, I would say, by Rose, Sulis, and Handa, who all happen to be University of Waterloo professors at some time. Fantastic book, hard to get a hold of sometimes, but it's on the shelf of all kinds of really interesting people that I respect. The picture of the cover on the left is by Henry Petrosky, who writes many great books about technology and engineering and design. This is a fun read on a work term. And Donald Norman has written The Design of Everyday Things, which was an earlier late 60s, I think, book, widely available, widely quoted. And it tries to be a little bit more detailed, but it's not as easy to read as Petrosky's book, and it's certainly less technical Bible-like than The Discipline of Design. But The Design of Everyday Things, great book. The cover may be different because they keep producing new editions. So I'm hoping that helps introduce you to design and makes you think of design as a discipline and gives you a hint as to why you'll be asked to go through these 5 steps repeatedly and routinely in any kind of design exercise, is that there's some very good reasons for those 5 steps. They're critical to good design. Thanks for listening.